Hi everyone. So as Chirag said, I'll be talking about two extensions to this language generation model that we've been talking about today. One thinks about generating with what I'm going to call diversity constraints. And so this is a paper called Representative Language Generation. And then another recent paper is on generating from noisy data. So when the adversary does not always give us points from the true language. So I'll start by talking about this first paper. And I'm going to offer a simple example to help us think about this notion. Here, I'm going to think about languages as sets of images. As we've kind of talked about throughout this tutorial, you can think of a language as sets of words, sets of integers, sets of images. Anything that has a finite representation is like a reasonable notion. And so let's think of a very simple language class that just has two languages. One is all the images of cats and dogs. And then the other is all the images of cats and rabbits. And so there's a common intersection here, which is cats. And a smart generator could leverage this to start generating validly from the true language without seeing any examples at all from the adversary. It could just generate a bunch of cats. And so as we've been talking about, this clearly doesn't have much breadth as a thing that the generator could output. It's not capturing either dogs or rabbits. But another way to think about a problem that might arise here is that the adversary's stream, let's say the adversary chooses language 1, could look qualitatively very, very different from the stream of images that the generator is generating. And so here, the data, you can think of the training data for this generator, looks like 75% dogs, 25% cats. Whereas the generator is just only outputting cats. And so really, even if these generations are consistent in some sense, they may not meaningfully represent the data stream. And this feels like maybe not quite what we usually care about in the real world, where arguably one of the key goals of generative models is to see some training data and then be able to generate data that actually resembles this training data in meaningful ways. And so we're going to introduce a definition meant to kind of capture this goal. And so at a high level, we're going to require that this generator's stream is going to match the adversary's stream with respect to proportions of some key subpopulations that we'll define. And in order to do this, we're going to make a small change to the model. So rather than just outputting a single element at each step, we're going to ask the generator to output a distribution. And this just means that we can get a sense of the generator's belief over many different items rather than just a single element. And we'll define our notion of diversity with respect to a collection of groups. And a group is just some subset of our domain X. And so we're going to predefine some collection of groups that I'll call this curly G. And so the requirement of representative generation is that for any group we care about, and at every time step t, the distribution that's outputted by the generator, so this mu t, has to satisfy a very particular constraint. And so in particular, for any group, we can look at what is the portion of the domain that this group covers, and we can compare this to what is the proportion that the mu t outputted by the generator is supported on. And so we'll care about, in particular, the proportion of that mu t that actually consists of members in that group G. And what we're going to require is that if we look at the same thing for the adversary, so if we look at the set of points that the adversary has outputted so far, we want this proportion that the generator is placing on G to be very similar to the proportion that has been outputted by the adversary. And so mathematically, it will look something like this. And so there's a few ways to think about this definition, and please stop me if you have any questions about it. One, it was inspired by notions of like group fairness. So you can think of this as saying certain groups that are well represented in the training data that the generator sees should also be well represented in the generations. You can also think of it as a notion of indistinguishability with respect to tests defined by these groups G. And so we're saying these generations should look indistinguishable from our data stream with respect to some coarse tests. And lastly, you can also think of it as a relaxed notion of breadth. in that if our adversary is outputting many points that cover many different groups in our domain, we're requiring that our generator is also capturing that. And so it's capturing some low coarse level of diversity, but not quite this like strict language-specific notion of breadth that Anne and Grigoris have been talking about. Any questions about the definition? Cool. So the natural question here is, for which collections of groups and collections of languages can we actually achieve this notion? And so the key theorem that we show is actually this is very possible for most sets of groups and languages. So for any countable language class and pretty much any group collection subject to a minor constraint, you can representatively generate in the limit. However, kind of akin to this non-uniform generation that we talked about earlier, whereas standard generation in the limit can be achieved with only this simple membership query oracle, you can't do this to do representative generation, even if you allow oracle queries to the members of groups as well. You really need a stronger oracle that thinks about how do the languages and the groups intersect, and is that intersection finite or is it infinite? And so we also characterize representative uniform and non-uniform notions of generatability, which kind of intuitively follow from the standard notions of non-uniform and uniform generatability for a specific class of groups, I should point out. So for only finite and disjoint collections of groups. And so to give just a small taste behind how we achieve representative generation in the limit, so this theorem that I just mentioned here is basically a small modification to this critical languages algorithm of Kleinberg and Mullyanathan that Moses mentioned earlier. And so this algorithm says, okay, let's list out all of these critical languages, find the rightmost, the highest index critical language, and just generate some unseen sample from that. And the problem with directly applying this approach is that the rightmost critical language may not actually have points that allow us to satisfy this representation constraint. So for instance, if we've seen a lot of members of a particular group that is actually finite in the most critical language, there's no more unseen members from this group to put in our mutee support. And so the small switch that we're going to make is we're going to filter out languages for which we can't achieve this constraint. So if there's just no way, we'll ignore it and assume that maybe we'll get to it later, or we just don't need to care about it. And the key idea in the proof is that in the same way that the true language eventually becomes critical, the true language also eventually allows us to satisfy these representation constraints. Not immediately, not even once it becomes a critical language, but at some point, and thus we can guarantee that eventually we'll satisfy representative generation. Cool, and so some future directions of this. One is going beyond finite disjoint group collections for uniform and non-uniform generatability, as well as understanding a full characterization of representative generation in the limit beyond just countable classes. And then finally, bringing things back to the real world, can we deal with groups that are more dynamic and maybe change or shift over time? And so moving on to the second paper, generating from noisy data, I guess I should ask, does anyone have questions before I move on? Yes?
Since the condition on the groups is pretty general, does that give you some kind of cryptographic indistinguishability between the training data and the generated data, because you can take all the groups that are, on the time computable or something like that?
Yeah, good question. I think you definitely could. The key assumption here is basically that not too many groups can have finite support in the true language. Only a finite number can. So as long as your indistinguishability tests satisfy that, then you're good to go. Yeah. I should say, though, that this is like not a computational result, though. This is more information theoretic. So if your cryptographic hardness is computational, maybe it doesn't make so much sense in the context of this theorem. Good question. Okay, so the next paper I'll briefly overview is this generating from noisy examples. And so the title is pretty self-explanatory in that all the models we've seen today have been in this realizable setting in some sense, in that the adversary is guaranteed to always output from the true language that it has committed to. But a natural question is, okay, what if that's not true? What if we relax this to allow the adversary to sometimes give noisy points that aren't from this true language? Can we still generate in this more difficult regime? And this is important for capturing real-world data sets where we might expect our data to be corrupted. One natural example is if we're scraping all internet data, this, without fail, is going to be corrupted by the generations of other LLMs with their own hallucinations that we'd like to ignore. And so in this new generation setting, we're going to allow the adversary to insert a finite number of noisy data points into the stream. And so more concretely, we'll start in the same way that the standard model starts. So the adversary is going to pick some target language and pick an enumeration of that target language. But then the adversary is going to pick some number, n star, and it's allowed to insert at most n star negative examples into the stream. And so I should note that it's inserting critically, not substituting. So this still is going to contain the entire enumeration of the true language. And from there, the game continues as normal. And one note is that this is not a new model. This was inspired by works that looked at noisy language identification. And so the model that they studied in the context of language identification was exactly this, of inserting a few noisy data points. And so the goal here is still the natural goal of language generation in the limit. At some point, the generator wants to be correct indefinitely at all time steps. And you can also identify notions of uniform and non-uniform noisy generatability, but I'll focus on this in the limit notion for this talk. And so one of the key theorems in this setting is that noiseless, non-uniform generation implies that we can noisily generate in the limit. And so this isn't quite the same as saying noisy generation in the limit is as easy as generation without noise. We do require the slightly stronger notion of non-uniform, but what it does tell us, for instance, is that all countable language classes are noisily generatable in the limit. And the authors also characterize noisy uniform generatability and provide a sufficient condition for achieving noisy non-uniform generatability. And so just a quick taste of how we get this sufficiency condition telling us that non-uniform generation is enough to generate with noise. The idea is, let's say someone gave us a black box model that non-uniformly generates, assuming the adversary has no noise. And so what does this model look like? Well, it takes in the entire enumeration that we've seen so far, and it outputs some time step at some generation gt at step t. And the guarantee is that there's some d star, such that after we've seen d star unique elements, this generator is correct. It's always going to generate from the true language. And so clearly this is all going to break when we add in noise. The generator may get some noisy elements. It's not clear how many are unique elements from the true language, and how the generator is or is not depending on these noisy elements. And so what do we do in this case? Well, the idea is we're going to introduce, we're only going to expose this queue to a sliding window of our data stream. And so in particular, Q is not going to look at the whole enumeration, but it's going to start from some threshold r sub t and see everything from that point on. And we'll use the generation from that point. And the key idea is that as long as the window size is growing, but also moving to the right, these two properties are very important, because the growing means at some point we'll see enough unique elements to trigger the non-uniform guarantee of Q, but also because we're moving to the right along this enumeration, at some point we're going to stop seeing these noisy points because we've moved past the last of these mistakes. And with a few tweaks to make sure that we don't generate any duplicates, this idea results in a generator that can generate in the presence of noise in the limit. Cool. And so some future directions of this work are complete characterizations of noisy non-uniform generation and generation in the limit. And also a natural question here is, so we know that standard generation in the limit can be achieved with membership oracle access, membership queries. We saw in Chirag's talk that this is not something you can achieve with non-uniform generation. And all we know so far is that non-uniform generation implies this noisy generation in the limit, but there's still this question of, is that a necessary implication, or is there a way to achieve noisy generation with only membership queries? And lastly, I think that one more open-ended question is, what's a reasonable definition of agnostic generatability? So even this notion with noise is still somewhat realizable in that the adversary is generating data points from the true language subject to a few mistakes. But it's interesting to think about how would we define a notion where the adversary itself is not constrained, but we compare our generator to a weaker goal that compares to some language class or something like this. So yeah, that's all I have for you. Thanks so much for listening. Any questions? Yes.
I was wondering what are some practical implications of the theoretical frameworks today, and maybe some pointers. Can we use the sliding window idea to create robust generative models? And do the results that we've seen today tell us something about possibility or impossibility of avoiding transformations in practice or in some settings?
Yeah, great question. Yeah, and also if any of this is like maybe one of the most foundational questions of these works. So if any of the other organizers wants to jump in, I think so. One thing I would say is that this is a very abstracted model, and so it's not going to capture a lot of the realistic concerns we have when training actual language models. But it does mean that the negative results in this model are going to capture these foundational barriers that maybe we can't hope to get around, even with some clever fine-tuning or these sorts of things. And so I think that especially these results on the contrast between breadth and valid generation speak to what maybe can we hope language models to achieve versus what can we not expect them to achieve. And also the positive results saying that generation is something we can do, whereas identification is hard, at least leaves the door open for language models to achieve things that would be useful for practitioners. Does that answer your question? The sliding window is an interesting question. I don't have a good answer for you. Yeah. Cool. Well, then maybe I'll hand it off to Chirag to wrap things up.
All right. Thank you so much again for